Welcome back. This is the Tutor Wizard. I'm Adrian. Please subscribe right here if you want. I don't really care. Linear Algebra 1. Chapter 3 is Geometric Vectors, Lines, and Planes. Section 3.6 is Lines and Planes in Space now, which is R3 essentially. This lecture specifically what we're going to do is we're going to give the 3 different avatars of a line and 3 different avatars of a plane. The algebraic ones, this is the geometric one, this is the geometric avatar. Let's get into what their algebraic avatars are, or what the horrible equations of these things are. In the next video, what we're going to do specifically is start interacting them and looking at properties of when are these lines parallel and when are these lines perpendicular and when is this plane and this line parallel and perpendicular, and we'll start interacting with the objects. This lecture is just going to deal with what are the objects, lines and planes in space. Let's do it. Alright, first of all, lines in space. What we're going to do is we're going to consider a line in space. First we're going to look at the geometric avatar, and if Mark will just, or lightning will strike you down, Mark will want to strike you down, but he want to use lightning somehow cleverly, and he will. If you don't draw a picture, how are you going to derive or make sense of any of these things? So the first thing we're going to do is start with the geometric avatar of a line, and then we're going to derive the 3 algebraic avatars of a line from this geometric avatar. First of all, what we're intuitively saying is it's through a point and parallel to some vector v in space. That vector v has 3 coordinates, which we're going to remember, which are from the ambient basis I, J, K. It's going to have coordinates A, B, C, and then we're going to derive the 3 different algebraic avatars from this scenario. The first one we're going to get is the vector form of a line. What we're going to get from that is we're going to notice that a line L consists of all the points P, X, Y, Z, such that the vector P naught P, this vector, is parallel to V. And what that tells us is, first of all, what are the coordinates of P naught P? P naught P is, as vectors, it's the vector P minus P naught. This is the vector P naught. This is the vector P. P naught, in the geometric definition of addition, P naught plus this vector P naught P is equal to P. So the vector P naught P is equal to P minus P naught. You said P and not a lot there in that last sentence, but this is what we're getting every time. Everyone says, why is it P minus P naught and not the other way around? Because it's the definition of addition in this triangle. Now, once I have that, what do I know about this vector? This vector is parallel to V, and it should hit a nerve from the previous videos. When are vectors parallel? When they're scalar multiples of each other. This is where we get the parameter T. This says that this has to be a multiple of V. And this, in fact, right here, or solving for P, which is the XYZ, this says that P is equal to P naught, a fixed point, plus T times V. This is the vector avatar of a line. Vector equation, they're going to call it. There's one, avatar 1, the vector form of a line. Now I use the fact that there's an ambient basis of 3 space, and then therefore that vector V has to have coordinates, and so do these guys. The coordinates of P naught are X naught, Y naught, Z naught. The coordinates of P are X, Y, Z, and the coordinates of V classically are A, B, C. Now I can, from this, opening that up, I can get the parametric form or the parametric avatar of a line. Why is that? Let's just state it. P is equal to X, Y, Z. P naught is equal to X naught, Y naught, Z naught, which is fixed. And we know that T times V is going to be scalar multiplication. It goes on to each coordinate. So that is going to be AT, BT, CT. AT's from Star Wars. It's AT, BT, CT. Now what do I do with that? This guy with those forms is going to give me what? X, Y, Z in vector form is equal to X naught, Y naught, Z naught plus AT, BT, CT. How do you add vectors coordinate-wise once you have them? So this is going to give me X naught plus AT, Y naught plus BT, Z naught plus CT, and now what we do is get rid of the brackets in the vector notation, and we say that this is going to be the parametric form of this line. And what is that? Let's move it up. Now what we're going to get is, from this vector form, we're going to get the, stripping that off, the parametric form of a line is going to be X, Y, Z equals X naught, some fixed number, plus a parameter T times A. or AT. Then we're going to have y naught plus some parameter times b. And then we're going to have a fixed number plus some parameter times the other fixed number c. And what that says is this is the line through the point p naught and in the direction of the vector v. This is where v is and this is where p naught is. And this is what you need every time to build the equation of a line. What do you need? Two things, a point and a vector in the direction of that line. There they are in the parametric avatar of that line. And then what we classically do to have a third one to make your life miserable, not really, that's probably not the reason, but it's a good after effect, it's a good consequence, is we now solve for the parameter t and put each of these three equations in an awfully symmetric looking form, and we're going to call that, guess what, the symmetric form or the symmetric avatar of a line. So what am I going to do in each of these equations? 1, 2, and 3. I'm going to solve for t. So how do I do that? X minus x naught, y naught minus y naught, z minus z naught, and then divide by a and b and c respectively. We're not actually dividing. If you get a 0 in these, this is abusive notation, you can still have a 0 in the denominator and lightning can't strike you down, nor can Mark this time, because we're not technically dividing by 0. That says one of the coordinates of your vector in the direction of that line has a 0 coordinate. So you'll see when we get there. Now what we're going to get is, this is going to say that x minus x naught over a is equal to t, and y minus y naught over b is equal to t, and z minus z naught over c is equal to t. And now Hypatia says if two things are equal to a third thing, they themselves are equal to each other. So these things are all equal to t, so they're all equal to each other, and we get rid of the t and then everybody forgets. But here's now the symmetric form of the same equation of a line, which is going to be x minus x naught over a equals y minus y naught over b equals z minus z naught over c. This is the symmetric avatar of an equation of a line. 1, 2, 3, 4. It's all describing the same thing. This guy. And then we got planes. Let's do an example. Example 1, let's find the parametric and symmetric equations of the line L through the point -1, 2, 4 and in the direction of the vector v, 1, 0, 3. So we're going to divide by 0. Lightning won't get me this time. First of all, let's draw a pic. There's L. It doesn't matter, it's in 3 space somewhere. This is 3 space. Everything I see is in 3 space at minimum. And then what we're going to do is there's my P naught. Oh, it should be P0, it doesn't matter. But in our notation, what we were using there, it is. And then what I need to do is, arbitrarily, I'm picking some other guy, which is x, y, z. That's how you cleverly get this. We're going to create this vector, which is p minus p naught. That vector has to be parallel to our vector v. Where's our vector v? This one, which they said v was 1, 0, 3 this time. Wherever that is, that's the scenario we now have. What that tells us every time is we know that p minus p naught is a multiple of v, so that says p minus p naught is equal to tv, and we get the vector form. I'm deriving it again every time. This is the easiest way for me to remember what's actually going on and not just memorize things. I memorize the derivation, not the consequence of the derivation. Therefore, now I get p naught is equal to, or p is equal to p naught plus tv. You can watch TV as you're doing this. TV as you're watching TV. Now this is the vector form. That's not really what I wanted, but it sets up the other three. In the vector form, when I put all the coordinates, I'll get the parametric form immediately from that. Therefore, this says that the parametric form is going to be x, y, z equals, equals, equals. What do I need? I need a point to create the parametric form of the line. Where is the point? -1, 2, 4. Where does it go? In the parametric form right here. So I get -1, 2, 4. Then what I'm going to do is I'm going to get plus, 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 t, 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 and then where it goes here, the vector that I had in the direction of that, my vector is times 1 times 0 times 3, and then usually we're going to clean that up, and we're going to say that x is equal to -1 plus t, y is equal to 2, and z is equal to 4 plus 3t. These are the parametric equations of the line. To get the symmetric form, we solve for t in each one of these, and to help you out, it bothers you. So when it's not there, you have to put plus 0t and divide by 0. Because we're all solving for t in these ones. I know we're cheating. So the symmetric form from these ones, solving for t, is going to give me x plus 1 equals t equals y minus, divided by 1 technically, y minus 2 divided by 0 is equal to t, and also this one will be z minus 4 over 3 will equal t. So divide by the 1, even if it's there. 1 times t, you still divide by the 1. If it's 0t, you divide by the 0, which you're allowed to do in this rare case. And you divide by the 3. And what does that give me? This is now the symmetric equations. What do those do for me? Now I look. Anytime you're given these in any different scenario, see, this might be shell-shocking, and now we're going to do planes also. This is the easy part. This is this description of the objects. In the next video, we're going to start saying, are they parallel? Are they perpendicular? Are they oblique? And then we're going to compare lines and planes and a line and a plane. One of these ones, don't use the wrong finger. But we're going to compare a whole bunch of stuff, and there's going to be 9 different cases, and then we have to find all these different conditions. And when is that going to happen? Well, first of all, you're going to be given lines and planes in either one of their avatars. So it's either going to be, for lines, it's either going to be the parametric avatar or the symmetric avatar. So if I give you this, where's the point that I need and where's the vector? The whole point is, the numbers on the top. That's p. What does that tell me? P naught is minus gives me -1, and then a 2, and then a 4. It tells me the information I need from this form. And where's the vector on the bottom? The vector on the bottom is this guy, v, and that says that you're not dividing by 0. The second coordinate of v is a 0, and that told me originally that v was this vector 1, 0, 3. Where are they here in the parametric form? The point that I'm looking for is right there. And the vector that I'm looking for is the numbers standing in front of the t's, including when they're 1s and when they're 0s, so the t might not be there. This is how you find the vector and the point to describe the line in symmetric and parametric form. Let's do planes. 2. Planes P in space R3. Consider the plane P through the point P naught this time, and now containing 2 non-collinear vectors u and v, so they're not in the same direction. And what we're going to notice this time is the plane P consists of all the points x, y, z, such that this vector P naught P is in the span of u and v. Why is that? U and v are non-collinear, therefore are a basis of this plane P. Once they're a basis, any other vector, this means that the vector P naught P, which is the vector P minus P naught, geometrically, just like we did before, or using this diagram again, just in case I drew it, because you always draw the picture. This has to be a multiple, it's in the span of this basis, so it has to be a multiple of u plus a multiple of v, a linear combination of these vectors. So there must be some t, such that we have t times u, plus some number s, where we have times v. And so this vector must be written like this way. And so this is sort of the vector form, but this is the 3 slightly different forms we're going to get for a plane. Once we're in the 2-dimensional object, we're going to have 3 avatars, but those 3 avatars are going to be different. This will be the first one. This will be the parametric avatar. Then we're going to have the normal form, and then we're going to have, basically moving everything to one side is going to be called the general form of a plane. Let's do the parametric form. Put in the coordinates into this now. We see that, what are we going to get? We're going to get x, y, z equals, just like for a line. We're going to need the point, x naught, y naught, z naught, and then plus t times a vector v or whatever. But in this case, what we're going to get is plus t, plus t, plus t. And then what is my vector? U, I called it. It doesn't matter which one, but u1, u2, u3, which are all numbers. I know it's shell-shocking at first, there's so many things going on, but plus now our other parameter, s, this is why we call them parametric, because there's s and t, which is the parameterization. And then we're going to have v1, v2, v3, the fixed coordinates of the vector v. And this is essentially the parametric form. This is the parametric equations of a plane now. What do you need to describe a plane? This time what we're going to need is, yes, we're going to need a point, and there it is in blue. And then I need the two pink vectors every time. From this avatar, algebraic avatar of the plane, we see that the number standing in front of t will be one of the vectors, and the other number standing in front of the parameter s are going to be the other vector. Regardless of what form you're in, you need two vectors and a point to describe a plane. You need a single vector and a point to describe a line. We're going to need the same three components to build the other two forms, the normal form and the general form of the equation of a plane. What do I need? I need two vectors and a point. Let's deal with the normal form and the general form of a plane now, and then we'll do an example and we're done for now. The normal form of a plane. For a plane P, a vector n is called a normal vector to that plane P if n is perpendicular to the plane. Or in particular, what that means is n is perpendicular to every vector in that plane, and that should hit a nerve immediately, hopefully, because that's where we're going to get the equation from, because that says that n dot product v will be 0. Then what I cleverly do is I notice that it contains this point p naught, and then it contains that arbitrary point p, which was x, y, z, so it contains the vector p naught p, and because n is perpendicular to every vector in that plane, it has to be perpendicular to p naught p, and this is where we get the normal equation. This says that n dot product with p naught p has to be equal to 0. And then depending on which coordinates we have, let's open that up a little bit. Classically, what we're going to do, unfortunately, is call n ABC, just like we called v for a line, where we're going to call n ABC in some ambient basis. You want to be in there too? Okay, Will has finally come around to see what's going on. She likes planes, not lines. I know. So what we're going to do with that guy, if n is called this, and then we know that p naught p, what are the coordinates of p naught p? They are x minus x naught, y minus y naught, z minus z naught from before. I know. And so when we put that in there, what are we going to get? That's going to give us a, b, c dot product with x minus x naught, y minus y naught, z minus z naught is equal to 0. Okay, go that. And if we want explicitly, these are all the normal forms, but the one that you're most familiar with is going to be run the dot product. It's this times this plus this times this plus this times this. And that's going to give me if and only if a x minus x naught plus b y minus y naught plus c z minus z naught equals 0. This is the normal equation. And if we simplify and bring everything to one side and call d negative a x naught minus b y naught minus c z naught, we can get the general form, which is going to be ax plus by plus cz plus d equals 0. And this is the general form of the plane. From here, again, what are we looking for? The information we need. The general form loses it in particular because d is actually, again, what is d? It's negative ax naught, the constant terms in this when you FOIL everything out. We'll do this in the next videos when I actually have to compute. But the most important part is in the general form, if they give that to you ever in a problem where they're saying compare these things or do these things, where's the normal vector to this plane? Well, we said n was ABC, so it is the number standing in front of the coefficients in the normal form. There's n right there, there's the coordinates of n. And where are they in the normal form? They are standing in front here. And then, of course, we can actually see, in this case, what the point that we need is also. And coincidentally, it's going to turn out, how are we going to find a vector which is perpendicular to two vectors in our plane if we already have them? We're going to use the cross product. So even though there seems to be only one vector here, how we're actually going to do this in practice is we're going to build n from u cross v. So you still need a point and two vectors to describe the normal form of the plane, because we need the cross product will involve u cross v, the two vectors, and then we'll need the point for p minus p naught. Let's do an example. We're going to want n eventually. All right, okay, so I'm drawing the picture as I'm religiously supposed to. Now what do I want? I have a plane P and it's through 3 points, so I didn't quite draw it right. Don't be shy, you can draw more than one picture if you want. So first what they gave me is a plane P. I want this scenario from what they gave me. So don't be shy, draw 2 pictures, all right? Then what I've got is they gave me 3 points. You don't have to be accurate to try and plot those in 3 space. Just, it says they're all in the plane. So let's put them in the plane. There's P, and there's Q, and there's R, because I said. So this one's going to be P, I think I just said. And then this one will be Q, and this one will be R. And then how from 3 points, I already started cheating, am I going to create 2 vectors? Well, I can do PR, and I can do PQ. And that will create U will be the vector PQ, and V is going to be the vector PR. Then I have 2 vectors. What do I need to build equations of planes? I need a point, which I'm flush with, 3 of them, and then from those 3 points I can create 2 vectors. I need 2 vectors and a point always to create any one of these forms. For the parametric, I need those specific 2 vectors and any one of these points, and I can immediately build the parametric form of the plane. And then for the normal form, n is going to be the cross product of u and v, because I need to now magically find some vector which is perpendicular to both u and v in my plane, and that's going to be exactly their cross product. And then I'll have used 2 vectors to create the cross product, and then a point to create p minus p naught, and then I take their dot product equals 0, and I get the normal form. Let's do it, enough talk. For u, this will be pq, which as vectors is q minus p, which will be as vectors 1, 2, 1, minus 1, 1, 2, which is 1 minus 1 is 0. I did it on purpose, so when I do cross product, I have a 0 coordinate. 2 minus 1 is 1, and 1 minus 2 is minus 1. Then for v, this is going to be pr, which will be as vectors r minus p, which is going to be r, which is 2, 4, 3, minus the vector 1, 1, 2 again, which is going to be 2 minus 1 is 1, 4 minus 1 is 3, 3 minus 2 is 1. So now I have my 2 vectors u and v. What do I need to create the parametric form of a plane, a point, and 2 vectors? This says immediately that x, y, z equals my point 1, 1, 2, and then t times u, which will be plus 0 times t plus 1 times t plus negative 1 times t, and then s times v, which will be s times 1 plus s times 3 plus s times 1. And normally we clean that up a little bit, and I'll write this as x equals 1 plus s, y equals 1 plus t plus 3s, and z is 2 minus t plus s. This is the parametric form of the plane, parameterized with t and s. Now, to build the normal form, we're going to have to do something entirely different. First, what I'm going to do is create n from u and v, and then we're going to do the dot product of n, dot product p minus p naught. Let's do that. All right, I have u and v, so what I need now is n. N will always be u cross v, because then it's perpendicular to both of these vectors. We see that, what is this? This should be Pavlovian almost by now too. I, j, k. I put u in the second row. This is u, so 0, 1, minus 1. I put v in the last row, 1, 3, 1. And then I compute the 3 by 3 determinant by cofactor expansion along the top row, I, j, k. This is going to give me I times the 2 by 2 determinant by blocking off row 1 and column 1. So 1 minus 1, 3, 1. Minus j times the 2 by 2 determinant by blocking off row 1 and column 2. So 0, negative 1, 1, 1. And plus k times the 2 by 2 determinant by blocking off row 1 and column 3, which will be 0, 1, 1, 3. Once I have those, 2 by 2 determinants are AD minus BC, so this is going to give me I times 1 plus 3 is 4, minus j times 0 minus 1 is, there's 3 minuses there, minus, minus, minus 1, so this is 1. And then plus k times 0 minus 1 is minus 1. And then everyone loses their mind when I do this, but I'll remind you once. This is 4 times I is 1, 0, 0. plus negative 1 times j is 0, 1, 0, and then plus negative 1 times 0, 0, 1. I use scalar multiplication and addition to bring that into a single vector, and I get the vector 4, negative 1, negative 1. I did all that work. Is it correct? It better be perpendicular to both of my original vectors, which means their dot product should be 0. Check quickly. The dot product of u cross v, or n, with my u is going to be 4 times 0 plus negative 1 times 1 plus negative 1 times negative 1, which is 1 minus 1, which is 0. So it worked. It's perpendicular to at least u. I'm going to guess v also. You can check for yourself. This is the correct vector n, which is perpendicular to both u and v, or their cross product. Now what do I do with that? Once I have their cross product and I have a point, everyone always forgets because they're so happy because they have the cross product, you also need p not p, which is the vector x minus a point, minus 1, y minus 1, z minus 2. Don't forget p minus p naught. Therefore, n dot product this guy equals 0 is the normal equation of that plane. Let's write that down. Right, now that we have n and we have p not p, this tells us that n dot product p minus p naught is equal to 0 is the normal equation. And for us, that's now going to give us what is n? 4, negative 1, negative 1, dot product with x minus 1, y minus 1, z minus 2 equals 0 is that equation. Now do the dot product on the left-hand side, and that is going to give me 4x minus 1 minus y minus 1 minus z minus 2 equals 0. This is the normal equation. And if you want to simplify everything out, we can get the general equation. That's going to give me 4x minus y minus z, and then we get negative 4 plus 2 plus 1 plus 2, which is going to give me negative 1 equals 0. This is the general equation. Ax plus by plus cz plus d equals 0. This is the general form. Where is the normal vector? 4, negative 1, negative 1. 4, negative 1, negative 1. The numbers standing in front of x, y, z are the coordinates of the normal vector in the general form. Please subscribe right here. I'll see you next time.